Now we already covered the two most important functions, which is the D function for density and also the P function for probability. Okay, let's move on. Now the third function I want to introduce is actually actually there are some simulation here, but because of time, I would jump over this part. Okay. So if we have time, we can go back to this part again. But as you can see that, see, the reason that we want to use simulation is that sometimes when we are using these theoretical distributions, we have an assumption, right? We assume that we already know the successful rate, right? But sometimes in the real business, we don't really know the process that generates the data, right? So actually, you are not sure about what type of distribution you are encountering, right? Okay, and in that case, usually you have to do simulation. Okay, for example, if we run into a situation like this, say you have a very complicated case. See, this is pi, for example, this is your profit, okay? And your profit would depends on V and X, okay? Two variable. If V is less than 2, then your profit is square root X. And if V is fall within this interval, we will have this value. If V is larger than 5, then your profit will follow this one, okay? And you also know that your V is follow Poisson, lambda equal 325, and you also know that your X follow this one, right? So you want to know the distribution of pi. It's very complicated, right? Okay, if you want to if you learn probability mathematics and you're if you are in the department of mathematics or actually statistic, right? You might know how to calculate this, right? Given this information, and try to derive the distribution of pi given the distribution of V and X. Okay. Suppose you have a very, very difficult. This is not actually very difficult, right? But in the business scenario, from time to time, you will run into a situation like that. See, right? Okay. So you know that you have two random variable that you know their distribution, but what you really interested in, what you are really want to figure out is actually a business scenario like this one. Okay, you have some variable that you know with no distribution, but pi you do not know. But in order to calculate pi's distribution, it's very difficult, right? Because there are cases, right? So you don't really know how to do that, right? So this is a very good way to kind of use simulation to do that, right? You can use the random draw, right? Okay, you can use a random draw, and you can random draw V k times, right? You can write a function, right, called pi trial, which means that our trial pi for k times, right? So you do a random draw, and here is actually just to realize this mathematical formulation, right? You can write a program to calculate this value. Okay, so because you define a function like this one, right? So if I call pi trial and I give it like 100,000 times, okay, so I can kind of random draw 100,000 times, and then I can calculate the distribution of pi, right? See? So you can see that when I try it 100,000 times, and at the end of the trial, I calculate its mean and I calculate standard deviation, right? So for 100,000 trial, actually I have after 100,000 times, I have the average is 18.2, and the standard deviation is 8.28. Okay, that is the way that we use simulation to deal with our complicated business situation. Okay, which means that the thing that you want to estimate, the thing that you want to calculate, by itself, it do not follow any theoretical pre-existing distribution, right? Okay. But actually you know the rule, right? Actually you know the rule. You actually know the distribution of this two variable, right? So in that case, you can use this random draw function, right? So you do random draw, and if you repeat this random draw enough of time, okay, you can still simulate the result, right? And do a good estimation for the non-standard distribution, right? Okay, you see that? Okay. So actually, I don't have too much time to cover this code in detail, but maybe we'll have time to do that, to do more of this in our later course. So in your homework today, you don't need to do the exercises in section 4, okay? Just jump over it. Just want to let you know that the usage of this R function is when you run into the case that the thing that you want to calculate, the thing of your interest, is not by itself standard. It's not by itself pre-existing distribution. Then you might use this random draw to simulate. And it is actually this approach, right? Okay. And the last function that we want to cover is this Q function, right? And usually this Q function, they are used to calculate confidence interval. Okay. Well, in our course, we actually do not care too much about confidence interval. Not by no means. I don't mean that confidence interval is not important, right? But we just do not have time to to cover it too much, right? Actually, confidence interval mostly it is used in the theoretical hypothesis testing scenario, right? If you learn inferential statistics, if you are using if you are doing some questionnaire, try to do some use some inferential statistics to establish some theory, then you'll need to do that. So it's more theoretical than practical, I would say so. Okay. But the way to use it is actually not difficult, right? As you can see here. Now, for example, this if we want to know the 95% confidence interval, okay, for normal distribution 120, okay, which means that we have a normal distribution of mean 100 and standard deviation 20, right? And I want to have a 95% interval that the value will fall within this area, right? So 95%, so we actually need to know the quantile at 0.025, right, to 0.975, isn't it? 95%, right? So in this side, in the left tail and in the right tail, we want to take 2.5% respectively. So in this side, in this way, we can actually see that the 95% interval of standard deviation, for normal distribution of 120 is within this range, okay? And there's an exercise, right? I want you to like kind of make a plot to show the 99%, 95%, and 90% confidence interval of X. Okay, you don't need to draw it so beautiful. Okay, you can like let's try to do some exercise. Actually, the code is here already. Yeah. See, the code is here. But you don't need to, this looks maybe too complicated, right? Okay. So, but we know that, in order to do the 99%, we need to deduct is this one, right? Isn't it? Okay, to do 95%, it's this one and this one. Okay, to do 90%, it's this one and this one, right? So this is the boundary that we want to draw, right? So so what we want to do, we actually can actually, because you want to draw a curve, right? You need to draw this curve first, isn't it? So to draw the curve, we use the normal, right? Because it's PDF. And so it's 50, 25, right? And then you need to give it a range, right? So so first of all, draw the density, right? And then you want to kind of like F lines, right? Okay.
Professor, what's a line?
Sorry?
What does it mean? A-B-L-I-N-E?
F line is actually I want to draw some line on the plot, right? So I want to draw this vertical lines, right? So it's vertical line is V, okay, equal to this thing, right? See? This is the, like, right? So actually just only like 2-3 lines of code can do it, right? But you want to make it very beautiful. You need to like do a lot of things. You don't really need to do that, okay? Try to do it in this way, okay? And I'll actually leave it for your homework. You got a point? Okay. All right, so so your homework today is to do B and C, and remember that for A808B, you don't need to do section 4 because we don't have time to cover it. Okay. We will do more simulation now after we cover regression and logistic regression. Okay? Okay, does that answer your question about the situation that we want to use the R function? The R function is usually we are using it for simulation. Okay. So this is what we have learned so far, right? Okay, what we have learned so far. Now let's think about some real case of application, right? So up to this point of time, we learn how to use this built-in R function for the operation of distribution, okay? But it's still like too conceptual, right? If we want to use it in some real business case, how it is like, right? I want you to get an idea about that, okay? That's for the rest. Now, before I go in any further, there are 4 types of discrete distribution which are very important, okay, for business analytics. But unfortunately, that I think in the business school we mostly when we are talking about distribution, we are using like normal distribution. Okay, we do not touch this discrete distribution. But actually, in business environment, the discrete distribution is, you will see discrete distribution more often than continuous distribution. Okay, because in business we are always, when we get the data, we always get the data. For example, the number of success, right? Okay, the binomial is actually when you repeat an experiment with success rate P n times, and the number of success, the distribution of the number of success, right? That is binomial. Okay, you have n, you have a P, right? And you want to see the distribution of the number of success. Okay, if you repeat experiment n time, then it can success 0 time minimum. It can success n time maximum, right? And from 0 to n, there's every integer has a probability, right? That probability is called binomial distribution. Okay? And the second one is called geometry. Okay? That is the distribution of number of values before the first success, while repeating the experiment of success rate P. Geometry only has one parameter, only have one argument, right? It's the successful rate, right? And you have the successful rate P, and you repeat it again. You do not stop until you success. Okay? So the number of value before you get that first success, okay? The distribution, so the numbers of value before the first success is geometry, okay? So you, for example, you flip a coin, right? And until you get the head, right?
How many times?
Yeah, how many times you get tail before you get the head? So what is the maximum number of time before you get the first head? What is the maximum number? there's no maximum, right? Yeah. It is not likely, right? Not likely, but it is possible that you can like throw 1,000,000 times,
And
still not get ahead, right? Okay? So actually when the P is small, you need to repeat a lot of times. But this is very important when you are doing operation management, because you want to know the failure rate. You want to know the waiting time, right? And that is so important in the operation management, right? And the third thing is called negative binomial. It's actually a generalized geometry. This is the distribution of number of value before the nth success. It's not the first success, okay? You repeat it like you want to stop when you have like, for example, 5 success, okay? So the number of value before you get the 5th success, okay? The distribution of the number of value. And again, it can go to infinite. Yeah.
But does it include the failure between the 4th and 5th and the 3rd and 4th?
No. For example, I flipped a coin, right? And I want to get 5 heads.
Continuously, consecutively 5 heads.
No, not consecutive. The 5th. No need to be consecutive. Okay, just n equal to 5, right? So if I throw 25 times until I get 5 heads, then the number of value is 20. You get the point? Okay, so that is for negative binomial. So it's actually a generalized distribution for this one. Okay, and then there's a Poisson. Poisson is the distribution of number of success given the expected value of lambda. Okay, there's only one parameter. This is a very interesting distribution actually. The expected value is equal to its standard deviation. Is equal to lambda. Okay, so sometimes it actually just simplified binomial distribution actually. If you the expected value is actually n times p, right? Okay, you do not know p, you do not know n, you only know the lambda. Okay, in that case you will use Poisson distribution. Okay, I don't really have time to cover this kind of things in detail, but just to give you some idea that in the business scenario, this is how they would use, right? But since we do not have too many times, I want to give you some real case, okay? So you have a better idea about how probability can apply to business, okay? Now, there's a very, very famous case in probability called death by horse kick. Okay, death by horse kick. Okay, so in the army, there are some corps, right? The unit of army, the corps. This data is actually from World War I. Okay, so because World War I, there are a lot of horse in the army, right? So in every corps, every year, some people are killed by horse kick. Okay, so and this is the statistics. Okay, the number of events per year per corps, 0 is 109. Okay, which means that in 109 corps, no one is killed. 65 corps, 1 people is killed, and 22 cases. In 22 cases, there are 2 people are killed, right? So these are the data, the historical data. They do the statistics, right? From some country, maybe UK or some country, right?
Sorry, Professor, what is corpse?
It's like a group of army, the unit army, corps, like I think it's like a unit of about, so it's like 8,000 people, something like that.
So when it's more people, there is less death?
No, it assumes that the corpse has about the same size, right? So it's a unit of army
So
about the same size.
109 is 109 corpse?
109 corpse years. So they may do the statistic like 5 years, right? Okay. So this number is actually event. We define the event per year per corpse. Okay. So so you can see that this is the kind of like this is count, right? It's the number of events, right? Happened. It's the number of times the event happened. 0 time, 1 time, 2 time, 3 time, 4 times. And this is just the unit. Okay? It's just the unit that we do the statistics. Okay? So first of all, if you see this data, okay, it's a discrete distribution, but which type of discrete distribution should I use? Right? That is the first thing that you ask yourself, right? So you can guess. You guess that maybe it's a Poisson, right? So in R, there's a package called VCD package, right? And within this package, there is a function called good fit. So you can actually fit the data. This data is actually very simple. It's just a vector, right? It's just a vector. So you use this data and try to fit it into Poisson. Okay? Try to do testing to test that if this data are different from Poisson. Okay? So like all of the hypothesis testing, there's a p-value, right? So if the p-value is like less than 0.5, 0.05, then we will say that this data are significantly different from Poisson. Okay? So in this case, the p-value is actually quite large, right? So we say that it's not different from Poisson. So we can treat the data as a Poisson. Okay? So if you want to use a theoretical, if you have empirical data like this, okay, you can actually try to fit the empirical data into a theoretical distribution. Okay? And when you fit it, you will actually tell you the parameter. Because Poisson distribution has a parameter called lambda, right? Okay. Once you fit it into a distribution, the good fit function will return the object, okay? And within this object, there is the parameter. So you can see that this data can fit into Poisson distribution of lambda equal to 0.61. Okay? See that? Okay. So what is the benefit to do this? Now we know that it follows Poisson distribution of lambda 0.61. So we can calculate it by this p function, d function, right? For example, if I want to know the probability of n number of days larger than 2, right? Larger than 2, right? So I want to use 1 minus the left tail up to 1, right? Isn't it? Okay. So you know that the probability of number of days larger than 2 is about 12%. Okay? So, see, this is the way, usually this is the way that we apply the theoretical distribution in the empirical cases. Because in empirical cases, in the real business cases, you have some real data, right? And you want to fit that data into a theoretical distribution. And after you do that, you can use this P function, D function, Q function to do some business analytic purpose, right? Now consider this case. If you are an insurance company, okay, and you want to design the policy for deaths by horse kick, and you need to know the probability of number of deaths larger than 5. Okay? If you're an insurance company, right, and you want to know the probability of number of days larger than 5. Okay. First thing is, can you estimate this probability from the data? There is no event occurred. The number of days never larger than 5. But is there a probability that number of days will be larger than 5? It is possible, right? It's just not happened yet. Okay, right? So an insurance company, the probability may not be large, but for insurance company it's important, right? Now you can use now you know that it is a Poisson distribution with lambda equal to 0.61. Now you can do the calculation, right? Can you do the calculation now? What can we do now? Actually, this number is wrong because they because I'm talking about larger than 5, and here we are calculating larger than equal to 5. Okay, so suppose that we want to know the number of days that larger or equal to 5. Okay, so what we do this, right? We use 1 minus the left tail up to 4, isn't it? So the probability is like about 4 out of 10,000, right? 4 out of 10,000 is actually a very large probability for insurance company, actually, isn't it? Right? So this is the way that we apply the theoretical distribution in business scenario. You get me? Okay? Which means, first of all, we want to fit the historical data into a theoretical distribution. And once you fit it, okay, then you can get the parameter. Okay, so you get the parameter, you can do the calculation. Okay, the thing that you cannot directly read from the data, you can use this theoretical distribution to help you do the estimation. That is the point. Okay, so today we learned a lot about the theoretical distribution, right? Okay, but that theoretical distribution can be connected to real data basically in this way. Okay, now there's one more example here. This is actually a federal paper. The word may, it means kind of like a uncertainty or probability, right? Okay. So you want to count the number of main per paragraph in a set of federal papers, right? So this is well, actually this is the number of event, right? That occurred 0 time, 1 time, 2 time per paragraph. Okay, you can see that. So first of all, we fit it into Poisson, okay? But the p-value is like very small, which means that this event distribution are significantly different from Poisson. Okay, so so you can try some other type of discrete distribution, right? For example, you try negative binomial. Okay, so in this negative binomial, as you can see that it is not significantly different, right? So you can treat this empirical data as a negative binomial with size and probability. This is the parameter, right? Okay, negative binomial have 2 parameters. Okay, so you know the distribution, you know the parameter, then you can do the right. You can do the estimation for your business purpose. Okay. So the way that we apply empirical data, business empirical data, to theoretical distribution, and then we use the P function, D function, Q function to help us do the estimation. Okay. So this is the step, right? And there are some exercise for you to do for your homework. Okay. So this week's homework is actually quite easy, right? You simply do 2 notebook, right? And put it in. I think I already. Yeah, you do this 2 notebook, and with this file name, you actually upload it to this folder, and that's it. Question? Okay. Well, unfortunately, I hope I have more time to give you more cases, but actually, it is very challenging to like doing probability like in 1.5 weeks, right? Okay, but I want you to get the feeling, right? What's important is let's go back to here. Okay, probability is actually a tool, right? It's like programming is a tool, right? And this is the way that we want to use the tool in our business scenario. Most of the time, we use data to build model, and we use model to estimate the future, right? To estimate the probability of future event. Okay, and as long as we know this probability, we can use program, right, and use simulation, so that we can see that for every alternative decision, what is the outcome of every alternative decision with this uncertainty, right? We can calculate their expected outcome, right? So as long as we know the expected outcome for every alternative decision, we can choose the optimum decision by choosing the best expected outcome. Okay? Now, don't get it wrong. The optimum decision would not always lead to the best outcome. Okay, not always lead to the best outcome, because this estimation would not eliminate the uncertainty. The uncertainty is still there, right? Okay, don't get it wrong, right? The uncertainty is still there. What we have is the expected outcome, which is the most possible outcome. Okay, still uncertainty is there, right? Okay, so if you are in a department, or if you are in the application of finance or financial market, right? And in that case, you need to know two things. You want to know not only that you want to know the expected outcome, you also want to know the variation of the outcome. Okay, right? Because risk is very important, right? So if you are talking about risk management, you want to know the expected outcome, and you want to know the variation of the expected outcome. Okay, but in our course, because we only have one semester, right? So for the following, in the following course, I will always focus on the expected outcome. Okay, so but don't forget that uncertainty is still there, right? And if you want to deal with the uncertainty better, then you will have to take risk management into account. But that I do not have time to cover. Okay, so for the rest of the course, we actually use this model to teach you how to use data to look for the maximum expected outcome. Okay? Okay, so that's all for today. I'll see you next week.